This presentation will discuss halogenation radical reactions. The learning objectives are as follows. We will discuss free radical reaction steps, halogenation radical reactions, specifically looking at chlorine and bromine, and also discuss the regioselectivity and the stereoselectivity of halogenation radical reactions. By the end of this presentation, you should be able to identify radical reaction steps, predict the products of halogenation reactions, and determine the regioselectivity and stereoselectivity of halogenation radical reactions. Free radical reaction steps are generally classified as either initiation, propagation, or termination. So in order for us to create a radical, we must have that initiation step. And so that begins with homolytic cleavage. So the initiation either begins with heating chlorine, or in this case, or bromine, or in this case, shining light on it using irradiated light. The next steps for a radical reaction are the propagation steps, and this is identified as moving radicals from one atom to another. This can occur via addition to a pi bond, a hydrogen abstraction, or halogen abstraction, or either elimination. And then that final step, which actually destroys the radicals, is considered to be the coupling reaction. So here, this is where you see two radicals come together, coupling, and they actually destroy the radicals. So there are no more radicals in this reaction. So again, the reaction steps are classified as either initiation, propagation, or termination. As I stated, in order for a radical to occur, we must have that initiator, and that's a molecule with a relatively low bonding dissociation energy, which will start that free radical reaction. And this is usually a halogen, and so we can either heat it or we can shine light on it, which will create two chlorine radicals. We can also have peroxides, which is usually radicals are formed by heating that. So specifically, we can look at acyl peroxides. So again, we can either use heat or irradiated light, and so that will initiate and start that whole radical reaction. We also have inhibitors, which are basically scavengers of free radicals, and they actually terminate those radical reactions. Here we see this step here, we have hydroquinone, and so it's considered to be a scavenger. So again, we have hydroquinone, and we see we have this radical. So the radical then does a hydrogen abstraction, which is basically a propagation step, and we form this resonance stabilized species here, and we get RH. So then step 2 begins that, we can say, another hydrogen abstraction. And so what we have here is benzoquinone. And so that's what we have. So it actually stops this radical reaction. So the initiator actually begins a radical reaction, and then we have inhibitors, which actually terminates free radical reactions. So let's specifically discuss the chlorination of methane. So again, radical chlorination produces alkyl chlorides. So again, we see that if we react methane with chlorine and we shine the light, then we'll get chloromethane and hydrogen chloride. So again, that first step is that initiator. And so here we're going to shine a light, and so we get that first step. And so we see here, again, we get homolytic cleavage, and so we will form two chlorine radicals. So after we have that initiation step, or that initiator, we begin our propagation step. So remember, that moves free radicals from one atom to the next. So since we have this chlorine radical, well, now we can have a hydrogen abstraction. Forming what we have here is a methyl radical plus hydrogen chloride. Again, step 3, This is considered to be a propagation step because now we have a methyl radical that will form our product, which is chloromethane, plus another chlorine radical. And then we can have that termination step. So remember, that termination step is where the two radicals couple. And so now, again, we have our product where we formed a carbon-chlorine bond. So basically, this is the mechanism by which you can make an alkyl chloride. So chain reactions, that mean products from one step are reactants for a different step in the mechanism. So polychlorination is difficult to prevent. So whenever you have an alkane and you react it with chlorine with irradiated light, we will get polychlorination. So we see eventually what happens is that you can get a mono-substituted, di-substituted, tri-substituted, or either a tetra-substituted. So we can get polychlorination, and that's very difficult to prevent. So with chlorination, it's not as regioselective. But when we discussed, in this case, the regioselective, we're talking about, in this case, when we're dealing with substrates that's more complex than ethane. So say, for instance, here we have propane. We can get multiple monohalogenated products. So in this case, we have propane reacting with chlorine with irradiated light, and so we get two products. So when we think about the mechanism, we're going to compare the intermediates formed after the hydrogen abstraction. So remember, we must have that initiated step. And so basically we will shine light on chlorine. So we're only going to begin after we have, in this case, the carbon hydrogen abstraction. So I'm going to see here. So now we have our chlorine radical. And so we can do a hydrogen abstraction. So here, we can have homolytic cleavage to give us so when we look at this intermediate, we see we have a primary and a secondary. So I want you to think about which would be the major product, the secondary alkyl halide or the primary. So remember, when we're talking about stability, radical stability follows that of the carbocation. Therefore, the secondary is more stable than the primary. Therefore, this would be the major product. And this would be the minor. So remember, when we're dealing with substrates that are more complex than ethane, we can get multiple monohalogenation products. And so when we're thinking about that, we always think about the type of radical or that radical intermediate. So remember, stability follows that of the carbocation. Tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. And so also remember that a allylic is more stable than a tertiary. And then in the case of benzylic, it's more stable than an allylic. So when we're looking at this and we're looking at complex structures, always remember the stability. So that will determine the major product. Now, when we're discussing radical bromination, the regioselectivity, radical bromination is even more regioselective than chlorination. So when we take propane and react it with bromine with irradiated light, we get 97% of the secondary versus that of the primary. And the difference stems from the reaction energetics. So we're looking at, in this case, the enthalpy, so to speak. And so also, which refers to the stability of this radical that we're forming. So remember the first step, which is the hydrogen abstraction, that's the rate determining step. So when we're looking at the difference between a primary or secondary or tertiary radical, when we're talking about the chlorination process, we see that the energy difference or the transition state is there's not a big difference. Therefore, that's why you're able to get polychlorination, because of that energy difference. There's not a big energy difference at all. We also see that this is actually, in this case, when we're looking at the primary, the secondary, that first step is not the energy difference of the transition. There's not a big difference. However, let's compare. When we look at the hydrogen abstraction and the bromination process, we see that this is an endothermic process. We see there's a big energy difference between a tertiary radical, a secondary radical, and a primary radical. So we recall here that the lower the activation energy, the faster this process. Also, the lower, in this case, we see the more stable. So the tertiary radical is more stable, so it's lower. However, this is an endothermic process, and you see it's much slower than that of the chlorination. But however, it's more regioselective. And you see the energy difference between the tertiary versus the secondary versus the primary plays a big difference. So when we're looking at this, the larger the halogen radical, the more stable and the less reactive it is. The less reactive the radical, the higher the energy barriers. So we see a primary, that energy barrier is much larger. Also, that means the higher the energy barrier, the greater the regioselectivity. So bromination is more regioselective than chlorination. So that is why we get more of the secondary than the primary, because the secondary, that energy barrier for the primary is much greater. So therefore, bromination is going to be more selective for secondary. So let's do some practice problems. Predicting the selectivity, where will bromination occur? So looking at this structure here, so again, radical stability is very similar to that of cation stability. So remember, tertiary is more stable than secondary, which is more stable than the primary, which is more stable than methyl. Again here, allele is more stable, and then we have the benzyl. So what we're going to do is look at our structure and identify. We're going to look at carbon-hydrogen bonds. And so we're like, if homolytic cleavage were to occur, what type of radical would we form? So we're only looking at carbon-hydrogen. So this would be a primary. This would be secondary. This would be tertiary, secondary, secondary, secondary. Here there are no carbon-hydrogen bonds, but this would be a primary and this would be a primary here. So the more stable would be here. So if, remember, bromination is more selective than chlorination, and so either we could use heat, or in this case, to form that radical. So our structure would be as follows. Bromination is likely to occur here because this would give us a tertiary radical, which is more stable, so it's lowering that energy. So bromination would occur at this carbon here. Another structure. So if we look, where would bromination likely occur? Again, we identify. If we were to do homolytic cleavage, we're looking at carbon-hydrogen bonds. We identified this would be a primary, tertiary, secondary, secondary, secondary. This would be a tertiary. Again, it follows the stability as I've stated here. So again, it would occur at this site. So this is where bromination can occur. Some additional practice problems. B 11.13, 11.27, 11.33 A through C. So again, remember that bromination is more selective than chlorination, and that has to do with the energetics. So remember, it's always after that hydrogen abstraction. So that's the rate determining step. So that's going to determine what type of radical we're going to produce. So remember, benzyl is more stable than allyl, which is more stable than the tertiary, which is more stable than the secondary, which is more stable than the primary, which is more stable than the methyl. So when you're identifying or trying to predict the selectivity of radical bromination, identify what type of radical that you will produce. And that will tell you where, because that's going to be the most stable. It's going to have the lower energy. Therefore, bromination will occur at that position. So now let's discuss radical halogenation stereochemistry. Again, when we're dealing with larger alkanes, something like butane or more complex, and we form a new chiral center, remember the geometry of that radical. So it's trigonal planar, so it's interconverting, and so we're going to get a racemic mixture. So whenever you have or you're forming a chiral center with halogenation, remember you're always going to get a racemic mixture. So remember, the process first begins with that first step. That's the rate determining step, which is the hydrogen abstraction, which produces a radical that can rapidly invert. And so then after that, you have a halogen abstraction, which occurs on either side of the plane with equal probability, thus giving you a racemic mixture. So again, we're going to talk about bromination. So we're dealing with something, a complex alkane. So again, the first thing we're going to determine is what's going to give us that more stable radical. So you identify, you go through the steps. You see primary, secondary, tertiary, or if it's an allyl or a benzyl. So that will tell you where bromine will occur. So we see here, we already have a chiral center. So in this case, we're still going to get a racemic mixture because it is going through that, in this case, trigonal planar. So remember, so halogenation can concur on the top or the bottom side. So when we're looking at this, again, we have a primary, secondary, secondary. This would be a tertiary, secondary, primary. So we see here that bromination is going to occur at the tertiary position, which is already a chiral center. So we're going to get a mixture of products. So remember, if you can form a chiral center with radical halogenation, you're going to always get a racemic mixture. So let's practice again, predicting the stereochemical outcome of radical bromination. Because remember, bromine is much more selective than that of chlorine. So when we're doing this, the first thing you want to do is identify the regiochemical outcome, meaning what will give us the more stable radical. That position will undergo bromination only in this case. So when we're looking at that. So if we look at this structure here, so if we're looking at this position here, so again, the first thing that we do is identify the regiochemical outcome, meaning the position that will undergo bromination, meaning the position that will give us the more stable radical. So if we look here and we're talking about, remember that first step is that hydrogen abstraction. So that means here we have a secondary, secondary, secondary. There are no carbons here. This would be a secondary. We have a hydrogen, so this would be a tertiary. So here, bromination would only occur at this carbon here. So basically, so if you notice here, the stereochemistry of this did not change. Only here. So this chiral center here, there was no change. So when we're predicting that stereochemical outcome, remember, because it goes through, or the geometry of a radical, goes through a species that can interconvert. And so you have this planar species. So halogenation can occur on the top or the bottom. So that's going to give us a racemic mixture. So let's practice again using this structure here. Predicting the stereochemical outcome of bromination. Again, what you do is identify the regiochemical outcomes. That means the position that will give us the more stable radical. So the one that gives us the more stable radical is where bromination will occur. So again, we have secondary, 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 secondary. This is tertiary. We could say this is primary. So basically, of all these positions, tertiary is the more stable, so bromination will occur here. If we look at this, this is our only product because it's no chiral center. So this is our only product. So let's practice another problem. Again, we're predicting the stereochemical outcome of bromination. So again, what you do is you predict or identify the regiochemical outcome, meaning which, in this case, with the hydrogen abstraction, which will lead us to the more stable radical. So again, primary, secondary, this is tertiary. There are no carbon-hydrogen bonds here, secondary and primary. So of these, this is the more stable, so this is where bromination will occur. So again, we have a chiral center, so we're going to get a racemic mixture.